The innovative metal casting process of the future is here today. Lost foam casting has been slow to develop, but is finally a technical and commercial success. The name Lost Foam refers to the process of creating a foam model of the casting and then replacing the foam with molten metal. The process begins with polymer beads, which must be expanded to a controlled low density for molding. The beads as purchased have a cellular structure and contain a gas or blowing agent, usually pentane. In a pre-expander, steam is used to heat the beads, softening the polymer and expanding the gas. Control of density and bead distribution is critical in this operation. After pre-expansion, the beads must be stored for stabilization before use in molding. A distribution system delivers beads from storage to the molding machines. Tooling mounted in a molding machine provides a cavity in the shape of the casting or a portion of the casting. The preheated cavity is completely filled with beads through fill guns. Steam is again used for heat and now enters the cavity through vents and further heats the tool from the back side. This causes the beads to expand into the voids and to fuse together. The fused foam and the tool are cooled by water and vacuum to allow the foam to be removed from the tool. Tooling is typically machined polished aluminum, producing very precise dimensions, and an unusual but smooth surface finish with precise detail. The tooling is exposed to only non-abrasive beads and steam temperatures, and usually maintains surface finish and original dimensional accuracy throughout an extremely long life. Foams are normally aged, usually in a controlled warm air oven, to stabilize the dimensions. Foams can be molded in one piece, sometimes using movable pulls. Multiple pieces can be glued together to form extremely complex parts with internal passages and detail sometimes not feasible in other processes. Gluing is normally done with special hot melt glue, printed on the parting line between foam slices. Excellent dimensional tolerances, appearance and casting quality can be achieved when flat glue lines are properly designed and when tooling and equipment have proper precision and control. Foam replicas are then assembled with a gating system to form a cluster of parts to be produced in one flask. This can be done manually or by machine. Foams or clusters are then dipped in a water-based refractory coating which covers all surfaces of the foam, including internal passages. The coating will now have an internal surface equal to the outside surface of the foam. The wet, coated foam cluster is then placed in a drying oven to remove the water. Ideal process control and throughput are achieved with dehumidification and internal humidity control. The coated dried cluster is placed in a special steel flask, either manually or automatically. Dry sand with no additives is then rained around the cluster and vibration is applied to the flask. Inside, the vibration of the flask causes a layer of sand near the surface to fluidize. In this layer, the sand flows around and into the inside passages of the foam. The sand level rises as additional sand is rained in. Below the fluidized layer, the weight of sand above, together with vibration, causes the sand grains to move closer together, compacting them. The vibration and the flowability of dry sand causes densities of the compacted sand around the coated foam to be 10 to 15% higher than in other sand processes. Proper control of vibration and sand fill can ensure low foam distortion and full rigid backing of the coating. Some systems use synthetic mullite in place of sand to further improve cycle times and dimensional tolerances. After fill and compaction, molten metal is poured into the cluster. As the liquid metal moves inside the coating, the heat energy causes the foam to liquefy, evaporate, and break down chemically. The temperature of the metal poured and the foam characteristics will determine how much liquid, vapor, and gas will be formed. Special coatings have now been developed for various types of castings, which have capillary action to absorb liquids, as well as permeability to allow passage of vapors and gases. Because there is nothing in the sand to burn out, creating collapse or mold wall movement, dimensions are very accurate. After the poured cluster is allowed to solidify, the flask can be simply tipped over and the unbonded sand flows out. No additional violent shakeout or core removal are necessary. Because the foam pattern is left in the mold, no parting line is needed. This allows orientation of the casting to be more flexible and permits clustering, which produces more parts in a given mold area. More parts per mold means higher production at slower mold per hour rates. The dry, unbonded sand is easily recycled with minimum energy consumption. The mass of foam is low compared to the binders burned out in other sand processes, reducing emissions. This makes lost foam an energy and environmentally friendly process. Because there are no cores, core defects and fins are eliminated.